sodium. Do these two analytes need to be controlled the same way? It's generally agreed that creatinine kinase has a quality specification of plus or minus 30%. The quality specification of sodium is much tighter, generally less than 3%. If we produce creatinine kinase and sodium results that are both 5% above the expected value, which would we be more concerned about? The sodium, of course. In this scenario, we need to control the sodium values more tightly than the creatinine kinase values. The process of determining how we should best control each analyte is called quality control design. More precisely, quality control design is the process of identifying what quality is needed for each test and what control rules are required to notify the laboratorian if the quality specification is not being met. This is a cost associated with ensuring quality. We want to ensure that we meet our quality specifications, but not waste money and effort on trying to improve tests that already have a sufficient quality. If our quality specification for creatinine kinase is plus or minus 30%, and our creatinine kinase test performs with a quality of plus minus 2%, we don't need to worry about improving creatinine kinase. We should instead focus on other analytes that are not in such good shape. Identifying appropriate quality specifications for each test is not enough for determining how we should control each test. We need to also consider our test performance. Going back to our sodium and creatinine kinase example, if our sodium results have a variation of 0.25%, but our creatinine kinase results have a variation of 25%, we'll need to control our creatinine kinase test more tightly than our sodium test. There are 3 steps to designing the quality control system for a test. First, we identify what's the appropriate quality specification. Then, we evaluate our test performance. And finally, we select quality control rules that are appropriate for our performance and quality specification. Determining what quality hierarchy. You can see that quality specifications specific to clinical outcomes are at the top of the hierarchy, and goals derived from current state-of-the-art are at the bottom. This does not mean that goals based on the current state-of-the-art have no value. It's just that the other types of goals have more value. Let's look at the 5 parts of the hierarchy in more detail. Goals that are specific to a clinical setting should be used before anything else. A quality requirement for very precise monitoring in a transplant patient should take precedence over a general regulatory-based requirement. For general clinical settings, 2 main types of quality specifications are recommended. Quality specifications derived from biological variation and those based on the analysis of clinicians' opinions. The basic idea behind quality specifications derived from biological variation goals is to ensure that a shift in a test can be detected. We need to keep the analytical variation significantly smaller than the inherent biological variation of the test. Another approach is to interview treating clinicians and ask when they would consider a change in a result significant. Ultimately, this allows the construction of a set of quality goals. Unfortunately, this approach is very time-consuming, and the results vary from clinician to clinician. Next in the hierarchy are recommendations from experts and professional organizations. These are preferred to performance goals derived from regulatory agencies and external quality programs. The least preferable type of quality specification is derived from the current state of the art. Current state-of-the-art generally refers to the median performance of a group. State-of-the-art is not related to the clinical settings. It simply focuses on identifying what the average quality of a test is. Half the laboratories in a given group will have higher performance. Goals may be expressed as a percentage, or a concentration, or a number of standard deviations. Examples might be plus minus 1 millimole per liter, or plus minus 3 standard deviations from the mean. If the goal is not a percentage, it must be converted to a percentage by dividing it by the target value and multiplying by 100. Each quality goal specifies some allowable distance from the target value. The target value is usually either a group mean or the mean of the control lot. In the United States, the CLIA laws form a set of quality specifications derived from a regulatory body. An example from CLIA is the platelet specification of plus minus 25%. For a group of laboratories evaluating the same specimen, each lab should report a value that's within 25% of the group mean. One of the deficiencies of most quality specifications derived from regulatory bodies is that there's little science behind the specification. Why is the U.S. CLIA value 25%? Why not 24%? A more scientifically sound approach is to derive quality specifications from medical requirements. However, there's no universal agreement on what the medical requirements are. Biological variation is an approach that uses the within-person variation and between-people variation of the analyte in question to derive the maximum amount of analytical error that can be tolerated without adversely affecting the value. For platelets, the within-person variation is 9.1%, and the between-people variation is 21%. It can be probabilistically computed that as long as the analytical response is within 13.4% of the target value, it will not have an adverse effect on the result. Dr. Carmen Ricos and her associates have determined the components of biological variation approaches. Quality specifications derived from biological variation have scientific references that they were computed from. Here are the 6 scientific articles that were used to derive the biological variation components for platelets. Once the quality specifications have been determined, the next step is to evaluate laboratory performance. The bias and imprecision for each test must be determined. Bias or inaccuracy can be thought of as the calibration difference between where a test is calibrated and where it should be calibrated. Imprecision is expressed as the coefficient of variation, or the analytical CV. In the technical literature, the analytical CV is frequently represented as S measure. In most QC rules, there's a trade-off between error detection power and false rejection rate. The error detection power is the probability of a QC rule of detecting an error. The false rejection rate is the probability that the rule will indicate a problem when none exists. The essence of good quality control design is to select QC rules that have sufficient error detection power to detect critical errors, but the lowest possible false rejection rate. To determine which QC rules need to be considered, we need to compute how large an error we need to be able to detect. Unless laboratory bias and imprecision are both 0, highly unlikely, the normally operating test system will have some baseline amount of error. This is called the current total error. We need to detect an error that, in addition to our current total error, will violate the quality specification. This error is called the critical error, or S-critical. If our QC rule detects when S-critical occurs, then we'll know when our test system is no longer operating within the quality specification. The S-critical value is simple to compute, given a bias, S-measure, and a quality specification. The Z-factor is a probability adjustment factor, usually set to 1.65 for 90% probability. Once we know what S-critical must be detected, we look for QC rules that have a high degree of probability of detecting it and a low false rejection rate. The error detection characteristics of a QC rule can be plotted in what's called a power curve. The vertical axis is the probability of error detection. The horizontal axis is the size of the error. In general, as the size of the error grows, the probability of it being detected also grows. In this plot, we're examining the power curve of the 1-3S rule when evaluated multiple times. The bottom curve is for a single evaluation. The top curve is for 20 evaluations. Notice that if the S-critical is above 4, the 1-3S rule would likely be suitable. Each QC rule also has a false rejection rate, or probability of false rejection. This plot shows the false rejection characteristics of a number of different QC rules. The vertical axis is the probability of false rejection. The horizontal axis is the number of times the rule is evaluated. Note that the 1-2S rule is above the other rules, and the 1-3S rule is near the bottom. A single 1-2S rule evaluation has a false rejection probability of about 4.9%, or approximately 1 in 20. A single 1-3S rule evaluation has a false rejection probability of about 1%. These computations will allow you to optimally select the QC rules appropriate for your laboratory. The main problem with them is the time and effort required to do them. In conjunction with Bio-Rad, Dr. Westgard has automated this process with Westgard Advisor. Dr. Westgard's algorithm has the performance characteristics of the most useful QC rule combinations, which can be used as a part of Bio-Rad QC management software. Given inputs of the TEA, bias, and imprecision, his algorithm will calculate S-critical and select the optimum QC rule that has sufficient error detection and the lowest probability of false rejection. Westgard Advisor automates QC design. Using Westgard Advisor is simple. Begin by configuring the quality requirements for each test. Then specify the QC data requirements. Next, Westgard Advisor guides the user through a 4-part wizard. Part 1 asks the user which lot or lots to apply the rules to. Part 2 asks the user to define a date range of data to use in the calculation for determining test performance. Part 3 asks the user to make selections regarding which control levels data to use in the calculation for determining test performance. Finally, the user makes selections regarding the group that they want to be compared to. Westgard Advisor then generates rules based on your selections. To evaluate the impact of QC design in a clinical laboratory, Dr. Westgard performed the computations outlined in this presentation for a laboratory that was using a 1-2S QC rule for all of its general chemistry tests. For the 18 tests considered, it was determined that 14 of them could use a 1-3.5S rule, In general, these tests were working well within their quality specifications. The other 4 tests had more significant issues. A 1-2.5s rule was selected for albumin, a multi-rule for chlorine and CO2, and a special strategy was developed for calcium. One of the most important aspects of QC design is that it clearly identifies which tests perform with